This is a video working through energy conservation examples. Now, I had given you an example, or actually a couple examples already, back in the video that outlined the idea of energy conservation. The examples that I gave you looked like this. We had one where there was a ball and it was going to fall a certain distance. And then we had another one where there was a block and it was going to go down an incline. And both of those were the same height, and what we found was that our final speed at the bottom was the same for both. So I want to be able to give you a couple more examples of energy conservation in action. So I gave you kind of the simple cases where we were turning potential energy that was MGH, that kind of potential energy, into kinetic energy. I want to do a problem that kind of does this ramp idea, just because we already know how to do the drop one. We don't really need a new method, though we can apply the same energy method to a new situation. I want to apply this idea, and this is a simple one, to this block and finding the speed when we are halfway down. So if this thing is a height of 2 meters and this is a mass of 5 kilograms, we're going to start from rest up here at the top, and I would like to know what is my speed when I reach this point, which is going to be 1 meter above the ground. So here we go. We're going to have at the top potential energy and no kinetic energy. Now we can do this problem a couple different ways, and I had told you before that you are free to choose any position to be a height equals 0. A problem like this, it's easy to jump in and say, you know what, let's let my height be 0 here, and we'll move on from there. After you've done these problems for a little while, you might instead decide, and this would be easier if I just set my height equals 0 at this location. But for right now, we're not quite there yet. We haven't been doing these problems for very long, and we're just going to start with this height equals 0 down at the very bottom, jump in with kind of the very immediate thoughts. So then we're going to have initial and final. We're going to have potential energy, kinetic energy, and then we'll say total. Okay, initial potential energy, that's going to be mgh initial. Initial kinetic energy, half m v initial squared, but that's 0. Final potential energy, mgh final. Final kinetic energy, half m v final is our unknown, squared. So before, we had these cases where we had all potential energy at the beginning, all kinetic energy at the end. Now we've got all potential energy at the beginning and a mixture of energies at the end, which isn't a big deal. So our total here, mgh initial, our total here, mgh final, plus half m v final squared. We're going to set those equal to each other, and we can start canceling. Mass shows up in every term, which is great. I'm looking for v final, so I'm going to subtract this whole term over to the other side. So over here I'm going to get g times h initial minus g times h final equals half v final squared. Solving for v final, I will get 2 times g times h initial minus h final, all under a square root, and I can plug those in. 2 times 10 is 20, we're going to get a square root of 20, which is about 4.5. So we're going to get about 4.5 meters per second. If we had instead looked ahead and said, you know what, let's make this my height equals 0, then in the end I would have an h final of 0 there. My h initial would be 1 meter, because I would be 1 meter up. So then in that case this would become 1 meter. This would become 0 meters, and 1 meter minus 0 meters is the same as 2 meters minus 1 meter. I would have gotten the exact same result. The only thing that really would have been any different is that I would have had a term here that wasn't there. It might have made my math just a little bit quicker. But that's it. That's conservation of energy with regular old gravitation near the surface of the Earth. And we will leave other examples for later.